Astronomy Day! It's Alan Tokunaga. He's an astronomer at IFA, the Institute for Astronomy. I love that name. I don't know why. I love the simplicity of it. I love the directness of it. IFAs. You could probably put that to music. Hi, Alan. How are you?
Oh, I'm doing fine.
Alan works on a lot of things at IFA, and he'd like to discuss some of the technology involved, some of the magnificent instruments involved, and we'll also talk about TMT. The reason is he couldn't possibly not talk about TMT. None of us could.
Not in these days, yeah.
Yeah, these days. So what are you working on?
Well, I work in infrared astronomy, and I'm currently the director of the NASA Infrared Telescope Facility. So this facility is supported by NASA under a contract, and the University of Hawaii operates it for NASA. So it's on the summit of Mauna Kea, and its primary duty is to provide support for NASA missions. So I brought some pictures with me that we can talk about some of the work we're doing with our telescope in the immediate, our own solar system.
Okay, let's see some pictures. I see a picture over there, for example.
Yeah, that's a...
What picture is that?
That's a picture of our telescope. The telescope is a relatively modest size for these days. It's 3 meters in diameter.
Mm-hmm. As opposed to 30 meters. That would
That's
be
right. 10 times.
1/10 of the
That's right.
diameter.
Yeah. And this picture is actually taken at night, so you can see the stars in the background. It's a beautiful picture. And look at the next picture. And this shows a photograph of the telescope itself at night. And the telescope itself is simply collecting light and focusing the light. And the light is focused on
This
instruments.
is your baby, isn't it?
Yes, that's the one I'm doing.
This is what you do.
That's the one I'm responsible for.
You embrace this whole thing with this telescope.
Yeah,
Okay.
it really is my baby. I have to take care of it.
I just wanted to clarify that.
But there's 20 other people actually helping to, doing all the real work of keeping it running.
Yeah, okay. So what's that orange structure there?
That orange structure is the telescope itself.
Mm-hmm.
What's not shown is at the bottom of the structure is the primary mirror that collects the light, and it brings the light, reflects the light up to a smaller mirror, which is near the top of that orange ring. That smaller mirror is called a secondary mirror, and it sends the light down to our instrument. Now, in the old days, the astronomers would look through the telescope with an eyepiece, and we don't do that anymore. So we have instruments that will collect the light and record it, much like the CCDs that are used in the cameras all around us.
Yeah.
And once it's collected,
an eyepiece wouldn't give you wouldn't get the same detail, and you wouldn't be able to record it.
and we couldn't record it. Yeah. That's right. And the eye is much less sensitive than the detectors we're using.
Yeah. And finally, it was maybe I'm wrong about this, but let me throw it at you. If there was something really bright out there, you would hurt your eye. No.
Well,
no.
I mean, no, really bright, yeah, like the sun.
Okay. You're not going to look at the sun with this?
No.
Okay.
So we collect the light, put it on, the light is focused on our instrument, which has a detector. The information is recorded and goes into a computer. Then the scientist could spend months just analyzing the data after that point. So I wanted to show another picture which shows the instruments in the back end of the telescope.
Okay, we're going to show that now.
Well, this is one of the instruments that we're actually building.
Mm-hmm.
It'll go on the back end of the telescope. Oh, that's not the 30-meter telescope.
It's not the 30-meter, just correct that. It's the name of our show is the 30-meter telescope, yeah. But that's we're really talking about the infrared telescope.
Yeah. And this is showing the inside of the instrument. And I wanted to show this picture because it gives you a feeling for the technology that goes into this instrument. And we're building this instrument in our laboratory at the Institute for Astronomy.
You know, I wanted to get to that point. I had the same thought as when you started saying that astronomers, as many scientists, build their own instruments.
Yes.
Because there's nobody around who can do it quite like them. They understand what they need.
Yeah.
And they sort of learn to be mechanics. They learn to be computer developers. Right?
We do whatever is necessary.
Whatever is necessary. And this is
Yeah.
an example of that
Right.
very thing.
Mm-hmm.
I need this instrument, I'm going to build this instrument, I'll find a way to do it.
Yeah. Yeah, and that's right. It's like a physics experiment.
Mm-hmm.
And this type of instrument has never been built before. I mean, this particular kind of instrument.
What does
And
it do?
It's a spectrograph. So it will take the light and disperse it into the different colors or wavelengths. But it works at infrared wavelengths.
So what is it going to tell you? What's out there in terms of the chemistry?
Well, the main
What
thing that
materials are out,
Yeah.
what you're looking at?
Yeah, the main reason it's so important to work in the infrared is that the many molecules have transitions or absorption lines in the infrared. So if you want to observe molecules, the infrared is a place to observe.
So you can tell the materials, the elements.
Yes,
You can tell what
the elements and the molecules. So
the dust out there, if you're looking
We
at a
can-
planet or an asteroid, you can tell what it's made of.
yeah, we can. That's right. Not with this instrument, but with similar instruments,
Spectrographs, yeah.
type of spectrographs, we can study the surfaces of asteroids and find out what they're composed of, and I have an image to show later to illustrate that.
Okay. So now you have this, the light comes in, or rather the infrared light comes
Yeah.
in, and it goes through a couple of mirrors, and it goes into a
Into a-
spectrograph.
Yes.
And the spectrograph, feeds data into a computer, yes?
Right. Mhm.
What do you do with the data?
I'll show you some examples. Let's see, maybe we can go to the next example.
sure,
which
let's
is
go to the
Pluto.
next.
We go to Pluto.
Let's go to Pluto.
Yeah, how about that?
ThinkTech, we don't fool around. We go to Pluto, bingo, there it is, there's Pluto.
Okay, now this image is showing an artist's conception of the New Horizons spacecraft flying by Pluto. And Pluto has a large satellite called Charon. Next week, on July 14th, the spacecraft will fly by Pluto.
That's Bastille Day.
I guess it is, yeah.
Aux armes, citoyens. Formez vos bataillons.
All right, whatever.
It's July 14th, yeah.
It's a revolution.
Yeah.
This is revolutionary.
Astronomical revolution.
Yeah. So Pluto was the 9th planet. It's now classified as a dwarf planet. So there are 8 major planets, and Pluto is a dwarf planet.
Say dwarf.
Dwarf planet.
It's the largest planet, but it's a dwarf planet.
No, it's it's not classified as a major planet because it has an irregular orbit around. It's a highly elliptical orbit around the sun. It's not like the other planets, the other major planets, and it's has orbital characteristics that are similar to other objects in the outer solar system.
So is that because it's far away from the sun, that the gravitational force of the sun can't keep it on a more regular
No, it's just a result of how the Pluto formed.
in the first place?
Yeah.
There
But-
we go, back to the beginning.
Yeah, but Pluto doesn't care what we call it, and
Okay.
so you can call it a planet if you like.
Call me Ray, call me Jay.
Yeah. In the newspapers, you're going to see just amazing photographs of Pluto. Now, the next image shows, and again, it's an artist's conception of what it might be like on the surface of Pluto. So we know Pluto is covered by ice, so this is showing an icy surface.
We've never been this close. I mean,
No,
as
it's
we
the
are
first
going
time.
to be on July
So,
14th.
yeah, so first time we're going to have real images of Pluto.
Yeah, that ought to be really interesting.
Mhm.
Yeah. Okay, so you think it's ice?
It's icy, we know that for sure.
When you say ice, Alan, do you mean like water ice, like H2O frozen?
On Pluto, it's more methane ice and nitrogen ice and CO ice. And I'll show the next, let me talk about this first and then I'll explain how we know that. And Also, what you can see is what looks like a very thin atmosphere. And we also know that to be true, that Pluto has a very tenuous atmosphere. And you can see Charon, the satellite of Pluto in the background, and the sun. And the next slide. This shows a picture from the spacecraft that's going to whiz by Pluto. It shows Pluto on the right-hand side.
This is a real picture. This
Yes.
is not an artist's rendering.
It was sent back 2 days ago. And on the right-hand side, you can see Pluto, and on the right-hand side, you can see the satellite Charon. And this is the first time we can see this kind of detail on these objects. And another thing that you can notice is that Pluto has a kind of an orange color, and Charon has a different color, kind of a gray color.
So this picture is taken by the spacecraft,
Yes.
and it's got to be fairly close to the satellite.
It's, I don't know how far away, but it's probably millions of kilometers away from
Oh, okay.
Pluto when this picture was taken.
Okay.
But you notice Pluto's reddish, and that's because its surface is covered by methane ice, and there's also a very tenuous methane atmosphere. And the ultraviolet radiation from the sun has been breaking down the methane. It's been producing hydrocarbons, and these hydrocarbons have a reddish color.
Sounds like climate change.
Yeah, it's a kind of climate change. And the satellite Charon has a different color, it's grayish, and we know from ground-based observations, in part from Mauna Kea, that the satellite has a completely different composition. It's icy, water ice. So they have completely different compositions.
Interesting.
Yeah.
And you can tell with the spectrograph.
Yes, and the next slide illustrates this.
Yeah, okay.
Okay, now this is an infrared spectrum. And on the bottom, you can see some numbers, 1, 1.5, 2.0. This is the wavelength in microns, or micrometers, in the infrared. So visible light is 0.5 micrometers. So we're at longer wavelengths than what we can see with our eyes. And this spectrum, you can see lots of features in it.
This is your telescope.
Yeah, this was taken with the IRTF,
Okay.
our infrared telescope facility.
Okay.
And you can see if there were no absorption, the spectrum would be flat. There would be no dips in the spectrum. So the dips in the spectrum are showing the presence of methane ice, CO ice, carbon monoxide ice, and nitrogen ice. And they're indicated, it may be a little bit too technical to discuss it in detail, but there's no ambiguity in what the composition is from a spectrum like this.
So but you have two axes. Okay, you have one on the left and one on the bottom.
Yeah.
What do those axes represent?
The one on the bottom is wavelength. So if you go to the right, from left to right, it's longer wavelengths.
Yeah.
And the vertical axis is intensity. So it's the how much reflected light we're seeing from Pluto.
Yeah. And this is a picture of Pluto.
No, this is a picture of a spectrum of Pluto.
A section.
A spectrum. So our spectrograph dispersed the light into the different wavelengths, and we record how much light we're getting at different wavelengths. And we plot it up, and this is what that plot looks like. Okay? And the dips are indicate specific molecules on the surface of Pluto.
Wow, this is really interesting. So this actually covers a broad area, and you're getting kind of an averaging of the different kinds of elements that are out there. But they're all elements we know. They're all on the periodic table, aren't they?
Well, they're molecules.
There's no surprise here.
Yep.
Yeah. The other thing is, can your spectrograph tell that it's ice? Or is it just
Yes.
telling us what the elements are?
No, we can tell if it's icy or gaseous. The information we have from our spectrographs indicate that we're seeing the ice on Pluto.
Smart, that's a really sophisticated piece of equipment. I bet that spectrograph could tell that we are about to take a break. That's Alan Tokunaga. He's with IFA, the Institute for Astronomy, and he knew we were going to take a break.
It's a great spectrograph.
We'll be right back after this short break.
Aloha, my name is Jim Sean, and I'm host of a show called Education Movers, Shakers, and Reformers. Each week, live streaming at noon on ThinkTech Hawaii, we interview people who have special insights into education, from early education through K-12, all the way through higher education and beyond. Both public and private are areas we're interested in. We dig deeper. We try to find out what it's really like to be involved in making change, advocating for it, how you reform, what people's philosophies are in reforming it. As I said, we're live streaming every Wednesday at noon on ThinkTech Hawaii. And later on, you can find these interviews on YouTube and on the Hawaii Educational Policy Center website. We hope you join us as many times as possible. Aloha.
Okay, we're back, we're live. The guy at my left is Alan Tokunaga. He is a scientist at IFA, the Institute for Astronomy, on Woodlawn Drive in Manoa. And he has his baby, which is a infrared telescope on the top of Mauna Kea.
Yeah, the NASA Infrared Telescope Facility.
And he gets to go there whenever he decides to go there, and he can get into this beautiful, beautiful location. It's really spectacular.
Yeah.
It must be almost pristine to go up there and see the sky.
Oh, I feel really fortunate to be doing what I'm doing and have a chance to be an astronomer and look out at the universe and go to Mauna Kea and look at the sky from the top of Mauna Kea.
Yeah, you like your job?
Oh, very much so, yeah.
So, okay, let's, you know what I get from all this is that astronomy is, it's very important to Hawaii, certainly very important to UH. And we are known globally for doing some really advanced work in astronomy. Yeah. And we have great talent in IFA, and we are well known for it. So that's just another, you know, gratification point for you to know to be in a group like that.
Yes.
So tell us more about your science.
Okay. Can we have the next image? This is the NEO image.
Okay. The NEO image.
The Near Earth Object.
Near Earth Object. Okay, we'll pass on. You want to talk about the Near Earth Object?
Okay. These are asteroids and maybe cometary bodies that come very close to the Earth. And some fraction of them will inevitably hit the Earth.
What's an asteroid?
An asteroid is a rocky body that orbits the sun. They're thought to be remnants of the solar system, and they never got incorporated into a planetary body. So there are thousands of them out there.
And sometimes they're big.
Some are 100 kilometers or,
That's
or
big.
larger. Yeah.
And they have hit the Earth before.
Oh, yes. And you heard about the dinosaur extinction.
Really? Was that because of an asteroid?
That's one theory, yeah.
Oh, interesting.
About 65 million years ago. And these impacts of the Earth will continue. So NASA has a program to identify all of the potentially hazardous asteroids and keep track of them.
And you can do that with astronomical equipment, too.
Yes, and we have the Pan-STARRS telescope, for example, Haleakala, and it's scanning the sky every night looking for these near-Earth objects.
And you can plot their course. It's like plotting something at sea, a torpedo, for example. You're plotting where it is, where it's been, where it's going, and then you know when it's going to hit something.
That's right.
Yeah. So, is it going to hit the Earth?
one of these asteroids will hit the Earth sooner or later.
So if it's, say, how big did you say it was, or one of these?
Oh, there's quite a range. There are many small ones, maybe rock-sized, boulder-sized objects are hitting the Earth every day, but they vaporize in the atmosphere.
Yeah.
The ones we're worried about would be about 100 meters in diameter or more. And
Because they won't vaporize.
they won't
They'll
completely
come straight down.
Yeah, they won't completely vaporize. They'll hit the Earth, and something bad is going to happen.
We're more populous now than we were in the day of the dinosaur. And so there's a fair chance that if it comes down in numbers,
Yeah.
and there is a fair chance of that, I take it, little ones, big ones all together now, it's gonna land on an inhabited area.
Yes. Have you seen a meteor crater in Arizona?
Pictures, I think.
Yeah, it's about a mile in diameter, and that was caused by an asteroid that was about 30 meters in size, and it hit the Earth. It's made mostly of metal, iron,
How big's the crater?
a mile in diameter.
A mile in diameter from a 30-meter.
That's right. Yeah.
Whoa. So that shows you what kind of damage can be done. I mean, if
Yeah.
that came down on 42nd Street in Manhattan, it would be a terrible price to pay.
And those occur, I believe, on the order of once every 1,000 years.
But what can you do about it? I mean, you can plot it and say, everybody off 42nd Street. But
Well-
that's about all you can do.
Yeah, but well, discussions are going on right now regarding how to alter the orbit of such an asteroid. So if we can detect them early enough, in principle, there are ways of nudging it a little bit so it misses the Earth.
You have to go up there.
Yeah, we have to go into space.
So you have to have a
Yeah.
spacecraft that has the
Yeah.
ability to catch up with it,
Yeah.
or rendezvous with it, and then use some explosive of some kind.
Could be explosives, or it could be gently pushing it somehow.
What's this picture?
Okay. Well, this is a picture of a NEO that came very close to the Earth. So you can see the Earth and the geosynchronous satellite ring, and it came just outside of the geosynchronous satellites.
And this is only last year, not quite a year ago.
Yes, and we took a spectrum of this asteroid or near-Earth object. Can I have the next slide?
Okay, there it is.
Yeah, there it is. Now, this is actually hard to read, so but you see wavelength, just like the previous spectrum. There's wavelength on the horizontal axis and intensity on the vertical axis, and it's in the visible and near infrared spectral range. And from this spectrum, we can tell what type of surface material it is.
What is it in this case?
It's a kind of rocky material.
Like
sil-
rock,
sil- like silicates.
Like rocks you would find on the Earth.
Well, let's say silicate-like rocks.
Okay,
They're-
but all the elements in these rocks we have here.
Oh yeah.
They're on the periodic table. of
Oh yeah,
elements.
silicates and oxygen. Yeah.
Yeah, that's interesting. So we know the properties then, and we can calculate what would happen if it hit.
Yeah, and we can measure the reflection of this from this object, so we can tell how big it is, and it's about 14 meters or 12 meters in size, in diameter. So
Okay.
this one, if it impacted the Earth, would probably burn up in the atmosphere.
Right.
Yeah.
What's the tipping point?
It's, I would say, I think it's between 10 and 30 meters.
Somewhere in
But it also depends on composition of
the
the.
exact material,
Yeah.
yeah.
This one is not, is a rocky material.
But if there were iron in it,
If it's iron,
Oh.
it could reach the surface.
yeah, because that wouldn't burn up so fast.
Right.
Well, I mean, we have some extraordinary technology here through your telescope and through the other ones. Tell us about the other kinds of technologies that are being used on Mauna Kea.
Okay, well, the really high-tech stuff would involve various kinds of detectors. These are both optical and infrared detectors, and also very long wavelength detectors that operate at a wavelength of about 1 millimeter. That's more like a radio detector. Right. So a lot of time and money goes into optimizing these detectors. So every photon that we can collect is recorded. And then another important technology is adaptive optics. This is a technology that allows us to eliminate the turbulence in the atmosphere. So if you can do that, see, in most astronomical observations, the images that we take are limited by the turbulence in the atmosphere. So,
When you say the atmosphere, you mean the atmosphere around Earth?
yes, right.
Because there is no atmosphere out in space.
Right. And the atmosphere disturbs the light, and so it's when we look at it on a detector, it's moving around, and that
So it distorts the picture you're getting.
makes it fuzzy. Yeah. So instead of having a very sharp image, we get something that's blurred, looks blurry. Yeah.
So this technology is what, computer technology?
No, it's optical. It's both optical and computer technology. So it will measure the turbulence in the atmosphere, how the atmosphere is changing the light that we're looking at, and it will correct for the turbulence.
We've made great strides in that, haven't we, in the past 20, 30 years? And
It's amazing.
Spectral imaging and all that.
Yeah. This adaptive optics is just amazing, and the Keck Observatory was a pioneer in this technology. And so if you can in the atmosphere, it's really like taking the telescope and putting it into space.
Yeah. You jump over, you're outside the atmosphere
Yeah.
now. It's like having a platform outside to look.
Yeah.
Okay, so let's talk a little, let's take a break. When we come back, I'd like to talk about the technology in the 30-meter telescope.
Okay.
And exactly why that, is different.
Okay.
You'll see, it is different. That's Alan Tokunaga. He's with IFA, the Institute for Astronomy, on Woodlawn Drive, part of the university. And his baby is an infrared telescope, but he's familiar with all the telescopes up there because he's an astronomer. I wish I were an astronomer. What an exciting life. And we're going to take a short break. We'll be right back. We're going to dive into the TMT.
Aloha, my name is Miley Scarpino, and I'm the host of the Empower Hour. If you're interested in health, nutrition, fitness, here on the island of Oahu, want to learn more about places to train at or different trainers available, then watch my show on Fridays at 3. We have a great time, and I hope that you'll come join us. Much aloha. Now go get swole.
Hi, I'm Chris Leatham, and I'd like to invite you to come and watch my show every Wednesday at 3. I'm interested in a variety of issues that have to do with politics and our local business economy. And I'd like to bring on guests who like to talk about everything from technology to social media to what we can be doing to improve our environment. And so I'd like to invite you every Wednesday at 3 to stay and watch my show here with ThinkTech Hawaii. And I'll see you there.
Okay, we're back. We're live. We're here with Alan Tokunaga at IFA. And we're talking about astronomy in general and getting a handle on some of the amazing things that have been made possible by technology. We haven't followed it closely enough, I think, in terms of the public perception of the technology in astronomy. But amazing things have happened. Technology has moved everything ahead, and it has moved astronomy ahead in a very special way. And the leverage is enormous because of the distances involved and the discoveries that are possible. So now enter TMT. The biggest, at the time it was originally, conceived anyway, it was the biggest telescope, biggest mirror, I guess, in the world. 30 meters is 90 feet across.
Right.
And that is huge. But why do we care that it's 90 feet across? What is the technology that gives us new leverage with this particular instrument?
Well, the why do you care part comes from the scientific case for the 30-meter telescope. And with a large telescope like this, it's possible to study the very beginnings of the universe. So it's possible to study the first stars in the universe and how they were formed, and the first galaxies.
Why do you say that? I mean, how is that? That's like a time machine.
Yeah, it is.
A time machine?
You could say that, because as you look further and further away from the Earth, the light takes longer and longer to get to us, and we can look billions of years into the past. That is, the light. We can look at light that originated billions of years ago and have now just reached us.
So, and we can't do that now.
No, we can do that. Yeah. I mean, so with a large telescope like a TMT, we can look further into the past.
Okay, and reach billions of years ago. And what would we see with it? I mean, what for example,
Yeah.
what would we see billions of years ago? What would be the surprise and delight that we might find?
Well, there's a number of questions. When you go back to the very beginning of the universe, there's a number of questions. For example, how did the first stars form? When
The process.
The process, yeah. And also we know that at the center of each galaxy, large galaxy, there's a black hole. And how did these black holes form, and how did they evolve? We can reconstruct the history of our universe with a telescope like the TMT.
I think I'm getting it, because if you look at the one that's billions of light years away, the process by which that solar system was created and that black hole was created is going to be, in all regards, well, in many regards, I suppose, the same as the creation of our own solar system, because the way solar systems work is they're all kind of created the same way.
Well, there probably were no solar systems in the very beginning of the universe, because the universe consisted of only hydrogen and helium, primarily. No heavy elements like oxygen and carbon. These elements were formed later by the first massive stars and subsequent stars. So the elements that are in our bodies were born in stars that developed over time, that were born and died over time. And in this process, heavy elements were produced in the center of these stars. And when they died, there was the really massive ones that exploded, and that allowed these elements to be dispersed throughout our galaxy. And by some complicated process, we're here. It's incredible.
Took a while.
It took.
You be patient.
In our case, it took 13.5 billion years, from the beginning of the universe to two of us sitting here in this room.
It was worth waiting.
Yeah.
Well, I mean, that is actually that's incredible. To be able to look back in time and see the way things happened, even though it's distant, it's not really distant, and it runs a parallel to the way things happen right here at home. And I can imagine, the kinds of thoughts that run through the astronomer's mind who will be able to see that and look at that data. Would you use a spectrometer in the same way?
Yes, there are plans to have spectrometers on the TMT.
So you'd see what was happening with the materials there. I wonder if you find new elements that in those days.
No, I don't think we'll find new elements, but we can analyze how the first galaxies were put together, for example. There are many theories of how the first galaxies were formed, and we can test those theories using the TMT.
Incredible. I mean, it really, it's an eye-opener like that wide.
Yeah.
And you'll be there. You'll be close to it.
Yes.
You'll be able to look at that data. And I think that probably the world will change because of it. I mean, it's not just a bunch of astronomers on the top of the hill.
Yeah.
It's because we will understand things that we did not understand before. We will understand the origin of the Earth, I mean, of the universe.
Yeah.
And that will change the way we think about things.
Well, I think you're entirely right. Maybe not in the way that you're thinking, but I feel what you said is correct. It will change things because in a research project like this, the most important thing, the most interesting things will be the things we haven't thought about yet.
Right.
So there will be discoveries with a telescope like this that we have not anticipated, and it's going to change everything.
Can you give me some examples of the unanticipated things we might anticipate? In general
that's
terms.
an impossible question to answer, actually.
I meant it to be.
But for example, 10 years ago, maybe 12 or 14 years ago, the first exoplanets were just beginning to be discovered. So if we're having a program like this, let's say 15 years ago, exoplanets would not have been discovered yet. And we'll be speculating what can be done, what we will discover in the future. But the discovery of exoplanets has really blossomed in the last decade. So we now know of several thousand planets around other stars. And the TMT is designed to study these exoplanets. The push right now is to find an exoplanet that resembles the Earth. It's a second Earth.
Ooh. And what does that mean to have a second Earth? And maybe you have a parallel development?
Well, if you believe there's nothing special about life forming on this Earth, if there were another Earth somewhere else, there could be life there too.
That's chicken skin.
Yeah.
That's what, I told you there was a program on last night on PBS about Arecibo, and they've been waiting for radio signals from another civilization out in space. They haven't gotten anything yet, but logically, the possibility exists.
That's right.
Many miles away, but there it is. And there's a kid by the name of, I can't remember his last name right now, but who discovered an exoplanet right here at Elani School. You know the story? I mean, and he got an award in the science fair for that.
No, I don't. The name doesn't come to mind.
Chris, I'll think of it in a minute. But he's a really amazing kid. We've had him on some of our shows. And so, I mean, I never heard of an exoplanet until then. What's an exoplanet again?
It's a planet around another star. So it's outside of our solar system.
Okay. So it just means outside, outside. Yeah.
And a telescope like a TMT can not only find these exoplanets, but they can get a spectrum of the atmosphere, and that'll be really exciting.
Yeah.
So,
I mean, this is pretty heady stuff.
yeah.
I mean, if the telescope TMT were built, and it'd probably take a couple of years to build it.
About 10, I think.
10, really? Is it that big? Wow. And then it was staffed, and then the best astronomical minds came to use it. And all the various countries were involved. It would be kind of a global beacon of astronomy.
Yes.
More than any, even more than your infrared telescope. And everybody would be looking for those unanticipated discoveries you're talking about. It would really change things. And it would change things for Hawaii. Hawaii right now, I think, is respected as a great astronomical center, both on the mountain and in IFA in general. Because you guys write a lot and you're publishing all the time about what you're finding in your data. But that would take it to another level, I think.
It would take it to another level. There won't be very many. There's maybe one more telescope in Chile that would be slightly bigger than the TMT, and there's the TMT. The TMT would be the only large telescope in the northern hemisphere of this size.
Would that be better than the slightly larger one in Chile, or is Chile better than the TMT?
Well, it could be debated. There are some reason to think that the site on Mauna Kea is better than the site in Chile. So to the extent that's true, the TMT will be very competitive, in fact, and may be able to do things the telescope in Chile cannot do.
Yeah. And I've heard it said that the beer in Waimea, and astronomers usually do like beer, is better in Waimea than it is in Chile. With all respect to Chile.
Well, I can believe it. I can't vouch for it, but I can believe it.
So what happens, just hypothetically, if this project doesn't go? You know, because it's in this kind of strange controversy, which the world cannot understand. The world simply cannot understand it. And let me say that I can't understand it either. Mm-hmm. And I don't know if you can understand it. If you can understand it, maybe you can explain it to me. But there's this controversy going on that seems to be imposing a political theocracy on the top of the mountain. Somebody wrote a letter to the editor and said, well, we got democracy or theocracy? What is this? But if that prevails and TMT is not built, this is a hard question. I never promised you a rose garden, Alan. If that telescope is not built, what happens? What happens to Mauna Kea? What happens to IFA? What happens to UH as a place in the sun of astronomy? What happens to astronomy globally? What happens?
Well, it would be a sad day for science and people of Hawaii if the TMT could not be built. It would send a strong signal to funding agencies and other countries that this is not a good place to promote astronomy and to go elsewhere. And for the existing telescopes, the danger is that investments to make these telescopes more capable, or to build new instruments, or to do different things, that funding will begin to slowly dry up.
You mean even for existing telescopes?
Yes, right.
Existing efforts here?
Mm-hmm.
Maybe even your infrared telescope for that matter?
Yes, I would say so. I mean, for example, the Canada-France-Hawaii telescope is considering a project to replace it with a more advanced telescope. There'll be no disturbance to the site. It'll have the same footprint. But the funding agencies may get cold feet if they see that the TMT had a hard time to be built or is not built yet.
What makes this so ironic is that when the TMT consortium came to town, which was in the middle of 2005 or 6 or something like that, they came and they presented at the Plaza Club, in this building, in this building.
Yeah.
And there was a woman, she was their representative, and she said, we only know one way to do it. We cross every I. I mean, we cross every T and dot every I. We follow all the rules, whatever the law says, we do it. And that is what we're going to do. And that is what they did. They went through all these years. People say 7, but I think it's more like 10. And they got their permit. Yeah. And then the trouble began to undo a permit that had been so costly and so time-consuming. Yeah. And you really wonder, if we are subject to a much more profound criticism, and that is that we are not a state of the rule of law. That you can come here and waste your time for 10 years and get a permit that is ineffectual after all that time. How can you plan any investment?
I think that's one of the questions that will arise, but I have confidence that we can go forward and that the laws will be respected.
Yeah, well, it's important in this country
Yeah.
to be faithful to that principle. It's hard to make progress without it. And I'm hoping that all those people who go to Astronomy Day every year at IFA, which is a glorious way to spend a given Sunday, is it? Or Saturday?
Sunday.
Will form an alliance of its own kind, of their own kind, and take a position on this. And I find that there's no real countervailing balance here, that you have only one shrill group on one side and the other side, is not shrill. So the result is it tips the wrong way. And I'm here to tell you that what we need is a progress alliance. In the meantime, I'd like you to come back sometime soon, and we can take stock again
Okay.
on the technology and on the status of this huge humankind kind of enterprise, which is so important to all of us.
Yeah, I'll be happy to come back and talk about it. Yeah.
Thank you, Alan.
Yeah. Okay. Yeah.
Okay, done.
Cut.